Okay. Thank you. Today I'm starting late because of my device is having some issue with that link. So I started right now. So this is last Saturday we actually discussed about some problems regarding the nucleus having the I value 5 by 2 to 7 by 2 transition. So how many uh, Mossbauer line we will get if EFG not equals to 0? That means we have the electric field gradient, and then basically there is changes of lots of states which is actually divided into they are not becoming the degenerate state that time. So they split it into some different I values or magnetic values, and depending on the EFG not equals to 0. And following that we have some state different state we will get, and that depending on the transition how many signals we will get, we get the 6 lines in the Mossbauer spectra, and the intensity ratio should be 3 is to 3 is to 2 is to 1 is to 2 is to 1, depending on which transition we are talking about. And similarly, if any nucleus with having more than I equals to half to different I values, that will also we can calculate very easily. The following rules we have to use that we discussed in the last session. So let's suppose we have I equals to 5 by 2. We in the assignment, your assignment you will get the one question about that. We have a I value equals to 3 by 2 to transition 3 by 2 to 5 by 2, and where the EFG not equals to 0. In that case how many lines we will get? So depending on that, so we calculate that. I actually used to do this calculation, and I found around 4 lines will get only. So how we can, so following that I'm coming to that. So furthermore we actually discuss about what is that, and then next we discuss about the some paradox in Mossbauer line, how it looks like, how it's coming. And then so this is the another we talked about. Depending on what is the structure, we actually can identify by help of the Mossbauer, and also we can also easily calculate the spin state of that iron system. We know that there is a, if there is a spin crossing over here, so let's suppose one complex that can actually form different spin state. Let's suppose we have a high spin to low spin to high spin, this kind of transition happening. So how we can identify this? By this help of the Mossbauer spectroscopy we can easily identify that what is the spin state of the my system. Followed by we talked about some data regarding the iron systems with the oxidation iron 4 oxo system, where the this iron 4 oxo, this oxide oxo species has been transferred to the alkene molecule. How this iron oxo molecule can be identified by the Mossbauer spectroscopy, where we found there is a huge shifting of the Mossbauer spectroscopy because of the scandium. There is a not huge, that is a minimum changes of the uh, Mossbauer spectroscopy by presence of this scandium molecule. This is actually acting as a Lewis acid which can coordinate with the system, and then that will actually helping the generation of this oxo species, and the increase the rate of the reaction. Okay. And then further we again also discuss about the another iron triazole based complex, not the triazole, it is the uh, four coordinated iron species, which is, and there is a some uh, there is some ligand ligand moiety which is actually coordinated with that. And then we found there is a iron 4 oxo species which in presence of the base, which efficiently transferring the this oxo highly reactive iron 4 oxo species which is transferred to the olefin group, and then it's forming the peroxo olefinic system, which is a olefin can get oxidized to peroxo and followed by following the formation of the di alcohol, or depending on whatever name profile we are providing. Okay, so this iron 4 oxide also you can monitored iron 4 I don't know, isolated by the Mossbauer spectra, where we had a huge changes in the delta value and delta EQ value, uh, where the presence of the iron oxide, that is iron 4, is there because of the delta value shifting towards more negative direction. That means we have the less electron density onto the my iron center. Okay, so now now we can further go forward, that there is another problem we discuss about that, in the assignment we have, we just talked about that, we have a transition. Let's suppose we have a transition. Where is my pen? Oh, okay, it's fine. Oh, sorry, I connected in another wrong device. Think it will work now. Yeah, it's fine. So we talked about there is a transition between in the Mossbauer, in the nuclear state transition is that transition I equals to 5 by 2 to, sorry, 3 by 2. This will be 3 by 2 to I equals to 5 by 2. So EFG and EFG not equals to 0. So how many transition do we expect? Okay, so we're supposed to calculate that. Just a minute, I can show the result, and then we will supposed to calculate this. Okay, okay, okay. Okay, so we'll start calculating. We have our initial transition is around, we have a energies over here, energy over here. We have a transition of equals to I equals to 3 by 2 here, to I equals to 5 by 2. Okay, so now question is the how many transition is possible. Okay, Okay, as EFG not equals to 0, so we have this 3 by 2 will get split it into 2, as we know. That is the here over here there is plus minus half and the plus minus 3 by 2. Over here also this will split into 3 here, because we have plus minus 5 by 2 plus minus 3 by 2 and plus minus half. Okay, so we have a transition from here to here, here and here, both. Okay, and then we have another transition from here to here, and also further and further. Okay, so we have a transition, how many? 1, 2, 3, 4, 5, 6. So total transition is the 6. Now question is, this transition I equals to plus minus half to I equals to plus minus half to I equals to plus minus uh, plus minus half from this I equals to 3 by 7 by 2, and then I equals to 3 plus minus 3 by 2 to I equals to plus minus 3 by 2. This transition are a degenerate transition. So we have 6 total transition of 6. From it we have a 2 degenerate transition. Okay, if 2 degenerate transition is there, so we have total, we will get total 5 line. Okay, that's all. Okay, fine. Then now moving to the problems, recent problems. Okay, now we are talk about the hydrolysis of ligand exchange reaction by monitoring the Mossbauer line. Okay, so we have some ligand exchange reaction over here. That is, we have the FeOH2 whole 6 and which is reaction happening in place of the KCN. We are making a complex. This is called FeCN whole 6, which is 4 minus, and there should be K plus, and this is the reaction. We are recording the Mossbauer spectra at 5 degrees Celsius. The reaction happening at the reaction monitoring in a 5 degrees Celsius. So first of all, now coming to the Fe6 Fe. This is the Fe2 plus, sorry, 2 plus overall. So we have a Fe2 plus system. And what is a weak field ligand? Fe2 plus D6 and weak field ligand. Okay, this is the weak field ligand. We have a and hexacoordinated we have T2G and EG. Okay, so T2G is there. We have a weak field ligand 1, 2, 3, 4, 5, and 6. Okay, now if there is a some electron, one electron is more non-symmetric or electron distribution, unsymmetric electron distribution in T2G level. So it actually follow John Taylor's distortion. Okay, and then it's forming something like this kind of no, this is no. Okay, so this will be filled up. Okay, so this is the energy and this is the energy. Okay, so we have a electron distribution, we have an asymmetric electron distribution, so we have a valence contribution over here. So we in EFG valence equals to non-zero. Now if John Taylor's distortion is there, so we have a iron over here, water molecule, water, here is the water, and Z of distortion waste. So there is a lattice parameter also here. So we also have the non-zero EFG lattice to non-zero. Okay, if lattice equals to non-zero, then then so total effective EFG will be large. Okay, and then we'll get delta EQ value, highly spirited Mossbauer quadruple splitting will be get, and then now it's forming the iron hexacyano hexacyanoferrous. So all the cyanide molecule here in the DFeCN whole 6 4 minus, so it will have a low spin system as cyanide is a very strong field ligand. Cn minus strong field ligand. So this D6 low spin. Okay, if D6 low spin, how will be my electron distribution? Here is the EG, here is the T2G. So low spin as low spin, we have with all the orbitals will be paired up and EG will be vacant. And then there is a EFG is to 0 valence for the valence, and all the cyanide molecule equally coordinated, equally distributed into the hexacoordinated with the iron Cn, direction C. So there is a there will be CM. Sorry, I am not able to writing over here because of okay. I can write it on defined position. Okay, I am writing over here. A small one. CN. CN. Okay, so there will be EFG lattice also 0. So we'll get only one line. So in the Mossbauer, what they are monitoring, this is velocity second, and this is percentage of transmittance. In the Mossbauer, initially they started with a Mossbauer line like this, with a large delta EQ value, and the delta value over here is this. This is the delta value if we OH2 or 6, and this is the delta EQ value. Okay, now following the reaction time time going on, first of all they got this kind of result. It's going down little bit the intensity, and followed by there is a another peak, another sorry, not this one. There is a small shoulder kind of peak found in the Mossbauer line. Okay, this is the time. And then furthermore, this is because of generation of the new system, that is not the hexacyanoferrous. Because of we know in the previous slide we discussed about the hexacyanoferrous, we have the only one line. So in one Mossbauer line. Okay, and here we are getting two Mossbauer line, which is delta value shifted towards more negative direction. This is delta nu. Right now I'm saying delta nu. Later on we will talk about what is that. Okay. Now as time going on, they are getting another line over it. It's going down. The first line, whatever the for the we supposed not to draw this line increases with the time, and the initial iron, this one actually decreasing. And more interestingly, there is another line which is actually found over this line. This line found during the experiment. Okay, and once the completion of the reaction, they found only this one particular line with downward downfield. This is, we are talking about delta of FeCN whole 634 minus. Okay, as it Mossbauer saying that in theoretically this is actually we have a one Mossbauer line. So now question is the what is this line actually refers for? What is this two line? What is that? Okay, interestingly, this reaction happening at that temperature. What is the temperature we are providing? The temperature is 5 degrees Celsius. Okay, so we'll have a line which is not identified initially. So what are the possible reaction pathway happening? So first of all, I change the color. Okay. So our initial is the iron hexa aqua. It's 2 plus. If you treat it cyanide minus iron, it's initially forming FeCN whole 5 H2O, and iron is in iron 2 state. There is no changes of oxidation because of there is no redox reaction happening, only the coordination complex formation. So exchange of ligand only happening over here. So this will be my 3 minus. Furthermore, as the time goes on, so this forming actually hexacyanoferrous 4 minus. This have a one line Mossbauer on my online in Mossbauer spectra, and this is actually the middle part whatever we found. This is showing the other factor. Okay, so how this is actually showing? So we have a as Cn minus is a strong field ligand, and D is that D6 system. So we have the splitting will be something like this: T2G AEG, and oh, this is the EG, and this is the T2G. Okay, so D6 system, all the pair of, and then we don't have the EFG valence is to 0. Now, as that this is a structure, if you talk about the iron pentacyano what ferrous, which is the structure is Fe OH2, other direction everywhere is the cyanide. So it has a lattice. So one ligand is replaced by the one ligand is still remaining over here, water molecule, and this is the not a symmetric system. So it has a EFG lattice will be there. EFG lattice will be non-zero. Non-zero. Okay. So we have a EFG non-zero, which is lesser than my Fe hexa aqua system. And here, interestingly, this cyanide molecule is a pi acceptor ligand. It pulls the d electron density. If it is pulls the d electron density from the metal center, there is a increase of the penetration power of the s electron density at the nucleus will be penetration power of the d orbital in on the s orbit on the s orbital electrons will be less. So there is a chances of more electron density at the nucleus. If more electron density at the nucleus, so our psi 0 square of sample will be higher, and we have a delta r by r value negative. So will the delta value will be more negative direction. Okay, so that's why we are getting the delta value of this nu, which is actually a Fe cyanide whole 6 water. This is the molecule 3 minus. The delta value shifted towards more negative direction, and then we have the uh, delta value actually delta eq value actually decreases because of the it has only the efg, not efg lattice is non-zero, and the efg valence contribution is the zero. Because of the strong field ligand, all the electrons are paired up, and dc system paired up electron system, we don't have the efg no valence equal efg valence. Okay, so this is the problem. Another interesting problem we have to discuss for, depending on that, we actually talk about the we can talk about the my other uh, based on that system we can talk about some research problem, current research problem. No, these are the research problem which is actually resolved in a past. In our current research problem, we have some different result. We can, depending on that, we actually discuss about it. Okay. So another interesting is that we have problem is that Q is the ferrocene. We all know the ferrocene, the structure of the ferrocene. Okay, we have a ferrocene. So what is the structure of ferrocene? We have a cyclopentadiene. We know cyclopentadiene we have, and if you reduce it by one electron, then you will get the cyclopentadiene anion form, which is aromatic in nature. Sorry. So we have a cyclopentadiene. Okay, this is the cyclopentadiene. Here we have a hydrogen over here. Hydrogen, and this is the hydrogen. If you treat with the base, it will actually forming, oh my god, bad drawing. Okay, this is forming the negative charge. We have it double bond over here. It's actually this negative charge actually resonating, and then it forming the cyclopentadiene. This is anion form. It's forming this negative charge. This is called as, we are calling it Cp. So in the ferrocene, how is the structure of the ferrocene? We have this negative charge, which is coordinated with the iron Fe, and then we have Fe over here also. This is stagger form. This is bad drawing. Sorry about that. Can draw it properly. Okay. Oh, it's perfect. Okay. This is the ferrocene structure. Iron is in iron 2. Fe is the Fe2. Okay. Now, initial state, if you oxidize it, it's formed. If you take a one electron from here, so it will form the Fe3 plus. So now the issue is that we have we have ferrocene. So what is the electron distribution over here? This is system over here. This is the point group stagger of D5D 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 point group, and it having the electron distribution of this d orbital will be like this, because of this is the energy gap we are talking about, and this energy gap is higher than this will be my E1G, this is A1G, and this is A1G as A1D dash, this is E2G. Okay, so and then we'll have the electron over here, all the electron are paired up, so we don't have the EF EFG of valence will be 0. Now we have a ligand anisotropic in a direction. Here we don't have the ligand over in this direction, this direction. We don't have the ligand. Only ligand is present in the in one particular direction. So we have a EFG high, EFG equals to EFG lattice will be present, will be non-zero, and then we'll have the Mossbauer quadruple splitting will be there, and then we will have the Mossbauer line about I can write it and throw it over here. This is velocity, Doppler velocity. Second, here is transmittance, percentage of transmittance, and it is showing a delta value of around something over here. I don't have exactly. It's around 0.53. Its delta value is 0.53. Okay. Now, and delta EQ value is around large delta value because of the E of lattice. It's around 2 point something. It's around 2 point something. Now, if we oxidize Fe2 to Fe3, so we have electron distribution over here. Energy. We have a 2 electron over here. We have 5 electron. Okay, now this is unpaired electron. It's actually doing a highly S equals to half, which is coupled with orbital motion result spin orbit coupling and give a EFG lattice EFG valence, sorry, FG valence not equals to 0, which is opposite to opposing the EFG lattice. Okay, as it is opposing to EFG lattice, so it is actually showing this kind of result. Okay, the delta value becomes the similar in similar. So it's this is the Fe3. So delta value should come at my negative direction, but as the CP ring is highly electron dense, if iron becomes oxidized to iron 3, the CP ring, which is providing the electrons to the iron center, and they are minimizing the extra positive charge at the iron 3, and then we get the result that delta value is not shifting. So we have the delta value of iron 3 in ferrocene. We have a very minimum quadruple splitting. It's around 0.1. So it looks like it's similar. So it's supposed to be something like this. Okay, this is it's a delta EQ value is around 0.1 millimeter per second. So it's looks like overlapping to each other. So we don't have the splitting of the uh, spectra. Okay. So but the iron 2 system, that is ferrocene, with where the iron is the iron 2, we have a large delta EQ value because of the anisotropicity of the ligand at the surroundings to the iron metal center, because of the we here top and bottom have the ligand. Sidewise there is no ligand, there is a anisotropicity in the ligand distribution in the direction of the metal center. So we'll have a delta delta EQ value is large. Okay, so based on that we have a problem. Say we have a some Mossbauer spectra. Can we identify which one is the which? Let's suppose we have a Mossbauer. We have a molecules, like we can draw it very quickly. So we can draw actual how it looks like. We we have ferrocene over here. Fe. This is the Cp. Ferrocene mostly like striker conformation. We have this is the O, and we have this is a benzene ring over here, and we have some similarly here also. We'll have similar kind of molecule. Oh no, this is benzene. Okay, and then we have a porphyrin over here, TPP. That is what is the structure. I can draw it over here. um, Fe. Oh no, first of all I should, we have porphyrin ring. We know, all everyone know this is the porphyrin. Oh, I can write it later on. Okay, it's a bad structure, so we can draw it. You have nitrogen, here is the nitrogen, nitrogen, nitrogen. Nitrogen over here. pH. pH. This is the phenyl group. Now we have a structure like this with a poorly conjugated system. And then we have here, here, here. Okay, so this is the iron TPP, Fe TPP, TPP. Okay, and here we have the all two PT. This phenyl group has the one phenyl group is actually like this. Oops, oops. And then this is the CP ring over here. This is how my system is. This is how I can write it like this. If you can write it similarly over here. So this is the Fe iron TPP. Okay. So now question is our Mossbauer spectra. What is the my Mossbauer line? We have a Mossbauer line, something like okay. Now there is a two part. Okay, so I can draw it properly with a different color. Here is the one part with a blue line. Okay, so other is the red line. So we have a delta value over here, one delta value here. It is around 0.35 and another delta value here. Oh, delta value is 0.35. Now another delta value, you can write it in a red color. Okay. So another delta value is over here. This delta value is 0.44. Okay, this is the problem we have. So now question is, which delta value represents which iron center? We have a iron over here. We know all along this is the iron 2. and this iron TPP in where this is the iron, Fe is iron Fe3. Okay, so now question is, so which one is the which and why? So now solve this problem. Problem is that we have a iron 2. As we know, iron 2 always come, the Mossbauer line will come at the more positive direction than the iron 3. That the first indication we got, the one delta value is showing 0.44 millimeter per second, another delta value is 0.035 millimeter per second. Which one is more negative direction? That means we have a plus 0.3 millimeter per second, which is more negative direction. So that is represents these two big line over here, these two blue indicated line, which is over here, this line. This is indicating the iron. Can this is the Fe3, and this is for the FeTPP TPP molecule, and these two lines, this line and this, because of the FeCP equal to, as we initially discussed in the previous slide, we have a iron tyrosine 2, where the iron is the 2, we have a large delta EQ value. Why? Because of the delta EFG lattice is non-zero, and which is very large. That's why we have a delta EQ value, large delta EQ value. Over here, for the iron CP, the delta EQ value actually 2.28 millimeter per second. That much large over here. And this, for the FeTPP, we have a delta value. For the iron 3, as we know that there is a generation of the Fe high spin system. Fe3 high spin system is the porphyrin system, and coordinated with the nitrogen, and other direction is the chloride. This side is the chloride, and this side is the chloride. Well, two chloride are there. So here the delta value is, we know, 0.35, and delta EQ value for this equals to 0.35 millimeter per second. Why? We have a, if you look into this, is a energy, we have a T2G level and EG level. T2G and EG. This is the high spin system. All the electrons are paired unpaired. So we have a symmetric electron distribution. You have my EFG, what I am writing. EFG valence equals to non-zero. Now in the lattice there is some little bit contribution, equals to 0. Sorry, only EFG lattice is non-zero, which is cancelling to which is very less, because of all the porphyrin are symmetric in nature, and then the upside and downside, the z direction, let's suppose porphyrin in a xy plane, and z direction there is a 2 chloride ion, so it's similar to, there is some symmetricity over there. And then as it is symmetric in nature, so we have a lattice contribution is very less, not that much. But in case of the ferrocene, we have a there is no ligand surrounding X-ray plane, only the ferrocins, only the CP rings up as a sandwich kind of structure we have. We don't have the any ligand in the side wise of the metal center. So that is because of the we have a large EFG lattice value, and here also we don't have that much in that iron TPP. We don't have that much of EFG, uh, electric field gradient for the lattice contribution. Okay, so it's there, but not that much. So because of that, we have a delta EQ value for iron TPP is only 0.35 millimeter per second. Okay, so this is the problem. So we able to know that this is because of the iron to iron, sorry, iron. Oh, and more interestingly, we can check this line and this line are symmetric. The intensity is very low, but however these two line are intensity very high. Why so? We have a two iron 3 center over here. Here is the iron TPP, iron TPP 2, and 1 iron 2 is for the ferrocene. So there is a ratio will be 2 is to 1. So iron TPP will be 2 and ferrocene will be 1. And then that actually indicates in the Mossbauer line there is a intensity ratio will be 2 is to 1. This is found in the literature. Now they also found in recent publication. Now with this they are trying to generation the iron 4 oxo system that we previously discussed, that iron 4 oxo can easily form and that can able to oxidize the olefinic group to make a peroxo system, olefinic peroxo system, and then that can easily oxidize my olefinic group. So they treat with some oxidizing agent which is uh, ido oxo species kind of thing. I don't remember exactly what is the structure. So they are trying to just making a iron oxo system with the help of the some oxidizing agent, and then they found this kind of, we have a ferrocene and then we have a this is, we can write it Fe, and this is the, sorry, we can write it something how Fe, Fe, yes, the shortcut version Fe, Fe. Okay, this is they are making and they are treating the oxidizing agent. Let's suppose this is the oxidizing agent, and then they will forming ferrocene is there. Fe, this is iron 4 oxo. This is also iron 4. Okay, and then they try to monitor the Mossbauer. The Mossbauer. How? They are actually getting a Mossbauer line like millimeter second velocity. And here is the percentage of transmittance. Okay, what they are getting? Can write it. Okay, so there is a three fragment over here. Let's talk about this one. And then we have another fragment over here, this green line, and another is the red line. Okay, red line is to represent each other, that is the, so we have this red line, we have a delta value around, so that means we have in this case the delta value, delta FeCp equal to, and then we have a delta value of over here, this will be Fe, can write it green, delta of FeTpp. Now we have a delta value of, which will come, okay, and what I am saying, we have a delta value, another delta value over here. This is the delta value. This delta value is for the Fe oxo species. Okay, this is the Mossbauer of three component. One is for the this red component is for the ferrocene, and this green component is for the FeTpp, which is residual iron 3, and then iron 4 oxo is the iron 4. We have iron 3, then we oxidize to iron 4. If it is iron 4, then it should come at the negative direction, and it's showing the some negative direction is the delta value. We can say this is the, we can write it over here. The delta value for this iron oxo species is around 0.03 millimeter per second, and delta EQ value for this actually 1.97 millimeter per second. Okay, that much of result they are getting, and they are able to detect their in situ generated this iron oxo species. This iron oxo species is a little bit stable, so so they are able to detect this iron oxide species in liquid nitrogen temperature. Okay, so why this delta value is negative, much more negative than iron TPP, that we basically know about the iron oxide species. This is the iron 4 system. So if it is oxidized to iron 3 to iron 4, then it should come at the more negative direction because of the less d electron. We have a much better electron density of s electron at the nucleus, so we'll have delta psi square value of sample, psi 0 square value of sample, which is large, and that means there is the large negative value That means we have a higher oxidation state, means we have more negative delta value. Okay, this is not exactly positive, whatever absolute positive or absolute negative. This is depending on the negative, which one is the more negative, which one is the more positive. That is the main we are talking about. This is not the absolute. There is a one reference point we are talking about, that is the metallic iron. With respect to it, how what is the value of 0, or with respect to that negative direction or positive direction. Okay, as like the potential we are measuring the potential. No, we are not able to measure the absolute potential. We can measure the potential with respect to something. So that is the idea. Okay, so and then why the delta eq value, delta eq value is so large? You can talk about, we can think about that. We have a system like, this is a green color, right? So we have a octahedral system where so we have a T2G and EG, iron 4 oxo system. What is the electron? 4 electrons, 1 2 3 high spin. See, this is not the exactly something like this. This is the pentagonal coordinate system. So we have something like this electron distribution over here. So we have one side is the oxo double bond O. So we have a EFG lattice non-zero, as well as EFG wow, EFG valence D4 system. D, D4 system, yes. D4 system E valence not equals to 0. Combined of them will have the delta EQ value of 1.97 millimeter per second. Okay. So this is the one of the example. Now there is another example is again they are actually making a iron oxide species, and they are try to isolate that iron oxide species. So what is the, they are also again taking a two metals, one is the nickel, another is the iron. So from here only iron can be monitored by the Mossbauer spectroscopy, and nickel will be silent. The Mossbauer actually giving the idea what is the characteristic of this oxo species actually generating by by external addition of the some electron acceptor. Okay, so we have iron porphyrin. This is a porphyrin. We can write it. This is not the exactly TPP. TPP is a tetraphenyl porphyrin we are talking about. This is different than the TPP. So how it looks like, we can draw it over here. This is okay. Okay, right. Nitrogen. Nitrogen over here. Nitrogen over here. Nitrogen over here. This is the porphyrin. This R is another porphyrin over here. This is the metal over here. I can write it over here. Fe. Similarly, we have another porphyrin, similar kind of porphyrin over here. This is the nickel. Nitrogen, nitrogen. Okay. Then they treat with this, some formation of the this OH pH XR. Okay, this is the iron 3. This is nickel 2. Okay, 4 electron oxidation is forming. This is Fe. This is again nickel, and then we have this is phenyl ring. This is R. This is the iron 3 we have. This porphyrin actually oxidized to dot radical plus. This is nickel becomes the nickel 3. Nickel 3, and we have a dot radical plus. This is how they are forming, and they record the Mossbauer spectra, how it looks like. The initially spectra is like we have this is the delta value we have. This is 0.39 millimeter per second. This is the Fe3 unoxidized. In ground in before oxidation, before oxidation. What is the delta EQ value for that? Is around 0.9 millimeter per second. Now 4 electron oxidation will have another color. 4 electron oxidation will have, this says 4 electron oxidation system. 4 electron oxidation product, and delta EQ value is 1.10 millimeter. Second, and delta value is something around over here, which is 0.25 millimeter per second. Okay, so if all are this is the iron 3 also. Now question is, why this shift of delta value of shift delta value shift on negative direction. 0. Initially that was the 0.25, 0.39 millimeter per second. Now this delta value shifts to more negative direction, that is 0.25. So why happening so? The question should arise in your mind. What is the reason behind it? You can find it. How? Go to the previous slide. We are oxidizing the the ligand site as well as which is attached to the another metal center, which is nickel 3 nickel 2. Initially it is the nickel 2. We are oxidizing 4 electrons. How who are taking the 4 electrons? Sorry, this will be oxidized is the dot radical. How this is happening so? So initially our system is the iron 3 nickel 2. It takes 4 electrons. 4 electron takes its porphyrin becomes porphyrin dot radical plus nickel becomes the nickel 3 and the porphyrin nickel porphyrin which is surrounding over here, which is actually forming a porphyrin dot plus. So total 3 electron has been taken by the porphyrins and nickel center. 2 porphyrins and nickel and 1 nickel center actually taking 3 electrons. Another 8 electrons has been taken from this oxygen molecule, and then it's iron 3 becomes the iron 3. It's not oxidizing to iron 4 because of the iron 4 generation is a highly oxidizing potential required. So this is iron 4 3 which is surrounded by a huge positive charge over here. So that means the ligand surrounding this cyst iron 3 pulls all the electron every direction possible because of the porphyrin is a porphyrin dot positive and which is connected with a, oh, this one is actually double bond kind of thing, which is conjugate. So nickel 3 is a highly deficient and which is also connected with another positively charged porphyrin system. So two positive electron deficient porphyrins rings connecting to each other, and one porphyrin is actually highly electron deficient nickel 3 center, followed by another oxygen molecule which is bind with the iron center, which is dot radical positively charged, which is positively charged. So huge electron deficient center surrounding the iron 3 center, previously which was not there. So that means we have a iron 3 in the both the case. One case iron center surrounding with a highly electron deficient ligand center. That means we don't have that much of the electron density of the iron 3. So if there is less electron density in d orbital, so there is a less chances of the little bit less chances of electron shielding effect of the s electron 3s orbital at the 3s orbital. So we'll have the more s electron density at the nucleus. That means my psi 0 square of sample value will be high. As a result, the delta value comes at the more negative direction. That's reflects over here that delta value for this oxidized species is around 0.25 millimeter per second, which was initially 0.39 millimeter per second. Okay, good. Satisfied? Your answer? Okay. Then now come to the delta equivalent. All the cases we have the similar electron distribution. Okay. And another case, here the iron 3, this iron 3 actually sounding this is chloride and this one is a chloride. Over here we have a chloride one side over here, and the side is the oxygen. So we'll have the similar valence contribution EFG. We have a and lattice contribution will be little bit more in case of the oxidized species. So here EFG lattice contribution is non-zero, which is EFG non-zero and larger than initial state. Okay, so non-zero EFG is there. We don't have uh, that much of electron density surrounding the iron center. So delta value shifts more negative direction, and then delta EFG lattice is higher than the my initial iron 3 center before oxidation. As a result, all everything is reflects over here. Delta EQ value is 1 shifts to 0.9 millimeter per second to 1.1 millimeter per second, and then delta value shifts to 0.39 to 0.25 millimeter per second. Okay, so to it, I will stop over here. So this is the strong fundamental evidence that we can whatever we can making in our laboratory that can be easily isolate identify by the Mossbauer spectroscopy for the iron system. So this is a very strong tool to isolate the iron center if present over in your any system. Okay, to it I will stop over here. So we actually discuss about what are so we discuss about some electron distribution or ligand substitution reaction is been monitored by the Mossbauer spectra and how it looks like, and following the how we can write the reaction coordinate, we can take a how the my profile product profile diagram should be. We can write it over here. This is the concentration, this is the time. So my initial one is the red. So the red one is coming with this. Okay, with the time. So Fe, this is FeOH 2 whole 6, sorry, 2 plus. Then we have a green one. Green one is something like this is FeCN whole 5 is 2. This will be iron 2, and then followed by green one. This is the FeCN whole 6 4 minus. This is the product profile diagram. We discuss about these things now. Based on we talked about the some ferrocene. how Mossbauer spectra looks like for the ferrocenium, how will we, what is the effect of the ferrocenium ion in the Mossbauer. And here we found that delta EQ value for the menocenium is 0.1 millimeter per second, and delta value is nearly similar because of the lots of electron density pushing towards the iron 3 by the CP ring, that is the cyclopentadiene ring. Okay. So, and then we discuss about some research problem depending on this ferrocene and iron TPP. This is tetraphenyl substituted iron porphyrin, and we try to monitor the oxo species which is generated during the oxidation of the iron generation of the iron 4 oxo system. And this system has been monitored by the Mossbauer spectra as well as the EPPs as well as the Raman APR. They are taking lots of different spectroscopic techniques to identify this iron 4 oxo species. Oxo species actually monitored by the this iron oxygen bond formation actually monitored by Raman spectra. Raman has a good spectroscopic technique to isolate this stretching frequency of this oxo species. And then we'll have some oxo species with the iron. So this iron 4 system can be monitored by this Mossbauer line, but the Mossbauer spectra shifting towards more negative direction, starting from the 0.0.35 for the iron TPP 35 millimeter per second for the iron 3 center, which is after oxidation and generation of the iron 4 oxo species. This delta value shifts to more negative direction. The delta value is around 0. Plus 0.03 millimeter per second, which is more negative direction as expected because of the higher oxidation iron comes at the higher negative direction, and followed by the EQ value, delta EQ value increases because of the lattice contribution as well as the valence contribution, uh, the electric field at electric field gradient. Okay. And then the ferrocene comes at their its position. So we'll have the delta value of ferrocene is around plus 0.44 millimeter per second, and delta EQ value for the ferrocene always the higher is around 2.28 millimeter per second. Okay. And then again taking another porphyrin based iron porphyrin based complex, which after oxidation, 4 electron oxidation, iron still remain as the iron 3, and the surrounding the ligand environment and the another supporting metal which is actually oxidizing over here, and which is monitored by the Raman in the Mossbauer. But then in the Mossbauer, it's showing that delta value shifting is only 0.25 millimeter per second. That means this is the iron 3 over there present, and the ligands oxidations happens, which is responsible for this uh, shifting, little bit shifting of delta value, because of lots of positively charged ligand center is present surrounding this ion center, and delta EQ value shifting because of the some lattice contribution, increase in lattice contribution of the electron density, lattice contribution at the EFG. So higher lattice contribution over the initial component. Okay. So to that, we'll stop over here. Next day, we'll again bring some new research problems, and we'll discuss some little bit about the Mossbauer and summarize. I'll try to summarize the CD and Mossbauer combined together, and to it, I'll stop it over here. Thank you. If you have any doubts regarding the solving the problems in the exams, in the your assignments, please try to reach me, so I'll try to helping out. Thank you. Thank you all. We'll meet last time in last another one session, which is in the next upcoming Saturday. That will be the end of the session, and we'll hope you are enjoying this Mossbauer and city spectroscopic all the lectures by the Professor Datta, and we try to solve some problems, and that's all for for today. Thank you for your attention. Thank you.